See, now that we have looked at the basic concept of probability with some things like the three different rules of probability, the addition, the multiplication, and the total probability rule, along with the Bayes theorem, now actually starts the space called as the probability distributions world. Right, probability is whatever we have discussed in the probability, it is for an individual event, right? Probability of getting a tail, or probability of getting some number on the dice. Now when I apply it to the real world, we are more and more bothered about distribution in the probabilities. Like, let's say if I toss a coin two times, what is the probability of getting 0 heads, 1 head, 2 heads? All possible occurrences and their corresponding probabilities. That is what we actually called as probability distribution. So the whole application of the probability is through these probability distributions itself. They are nothing but any event that we are doing. Let's say I'm having having a, a set of policies, right? What is the probability that a given policy that I am taken will have a claim of more than 1 lakh? Will have what is the probability that a policy will have a claim between, let's say, 50,000 to 1 lakh? What is the probability that the policy will have a claim between 20,000 to 50,000? Below 20,000. So based on the data, I'm making a kind of a tabular form, right? So that is what we associate to what we call as probability distributions. Finding out all possible values when a particular experiment is conducted, find out all the possible values along with their corresponding probabilities. So that is what will to do that. Then the next chapter, typically this is the third chapter we are dealing with. The fourth chapter actually is a list of all the probability distributions which we are going to use. Almost 15 different kinds of probability distributions are what are being discussed in the next one. Something like a binomial distribution, normal distribution. There are good number of distributions, out of which at least 15 of them we are going to discuss in the next chapter. But to make ourselves comfortable to understand those distributions, some of the basic concepts are very much required. And that is what is this chapter called random variables discussing on. As the word itself is saying, we are talking about random variable. Any variable which can take any value which is more random in nature. Which means I'm not sure what value it can take. Let's say when I throw a dice, I know that it can take either 1, 2, 3, 4, 5, 6. But I don't know which one will come. In a random basis, one of those 6 values are going to come. That means when I throw a dice, getting a value on the dice, I can call it as a random variable. A random variable x is nothing but getting a 1, getting a 2, getting a 3, getting a 4, 5, 6. Let's say when I throw a coin 2 times, when I toss a coin 2 times, I don't know whether I will get 0 heads or 1 head or 2 heads. Any of them are possible. So I may say getting a number of heads is a random variable whose possible values are either 0, 1, 2. That is how we define a word called random variable. So any rule that we are trying to define, here I am more interested in what are the possible values that a particular experiment can take. So probably if I'm talking about the same claim scenario, right? The possible values a particular claim can take could be anywhere between 0 to 10 lakhs or 1 lakh. If I say the upper limit is 1 lakh, I can very well say that any particular claim, or if I say the deductible is somewhere around 1000 rupees, then probably I can say any particular claim can take any value between 1000 to 1 lakh. So there are so many values. When there are so many values, we are calling that particular random variable as a continuous random variable, because any particular value is possible between 1000 and 1 lakh. Whereas when I am throwing a dice, only 6 values are possible, right? Finite set of values, and I can easily count. I can easily identify what are the various variables possible when a particular dice is thrown. In that case, we call those kind of variables as discrete random variables. But whatever it is, whether it is discrete or continuous, understanding the word called random variable is nothing but a particular variable which can take values in a random manner, right? In a claim, when I want to do some kind of a model on a claim, I want to know what are the possible values that this particular claim can take. Any particular claim can take. So I can say it can take anywhere between this and this, right? But when I say, when you throw a dice, what are the possible values it can take, right? So that is what we are trying to call as the random variable. So typically we denote the random variables like this. We actually use a capital letter X or Y to denote random variables, and the possible value it takes. So generally if I write something like this, what does this mean? The probability that a random variable X takes a value equal to some X. So basically when I am tossing a coin, the probability, or when I am throwing a dice, the probability that X is equal to 2 means the dice gets a value of 2, right? The dice gets a value of 2 is 1 by 6. There are 6 possible outcomes, out of which 2 can come as one of the outcomes. So the probability that X takes a value equal to 2, I say as 1 by 6. And this is what the way we represent. This is my random variable here. X is, so how do I define X here? X is the value that occurs when I throw a dice. Because that number can be any of the 6 possible, I call it as a random variable. I don't know which one will come at what point in time. That's the reason we call that variable as a random variable. So just like that, in a claims world, if I pick up one policy, I don't know, the claim could be any number. If I have a list of policies for which I have received the claims, at random I pick up one claim, and if I see there could be any number in that claim amount. Or if I am seeing the life insured, what is the sum assured in this policy? It can be anywhere between something to something, right? In these kind of cases, we are calling them as random variables. So the probability that this random variable will take a value equal to 2 is equal to 1 by 6. Or probability, when I'm saying Y is a random variable where of tossing a coin. So, and if I say the Y tossing a coin and getting a head, right? So getting a head, so getting one head right? The probability that it takes one head is equal to 1 by 2. The probability that it takes 0 heads, because I have defined the event as getting a head. So 1 head, the probability is 1 by 2. 0 head, the probability is 1 by 2. So that is how we define what is associated with a random variable and how do I represent the probability associated with the random variable. That is where we are saying this is denoted by a capital letter, and the possible values it takes, it is denoted by small letter like this, right? Then, so discrete is nothing but throwing a dice, tossing a coin, where I can count how many outcomes are really possible. So that is what we are calling as the discrete variable. Now with that, so first when I identify a particular variable is continuous or discrete, so which is nothing but if I know that number of outcomes are finite, right? I can count how many possible outcomes are there easily. I call that to be a discrete variable. Otherwise, I'll call it as continuous. If I can't say how many different values can come up. For a claim, I don't know how many different values can come up. If it is rounded up to some paisas or something also, the amounts could be completely different. Or even if I can count it, but it is very large, then also it's better to assume it as continuous itself. Only if there is a very finite number of outcomes, I'll look at it as a discrete random variable. So like this, just now whatever we have discussed, the probability that x takes a value equal to 1 when I am rolling a dice is 1 by 6, right? Now, in this context, it is very much important for us to understand one item called as a probability function. It's also called as probability distribution function. What does it mean? A simple example. Again, when I am rolling a dice, right? I am making a kind of a table here. I am making a kind of a table here. Okay, x is a value that comes when I roll a dice. So what are all the possible values x can take? 1, 2, 3, 4, 5, 6 are the various possible values x can take. And what are their corresponding probabilities? All are 1 by 6. Right? Getting a 3 is 1 by 6. Getting a 4 is 1 by 6. Getting a 5 is 1 by 6. All of them are 1 by 6. If I make a possible table like this, wherein I am considering all the possible outputs, possible outcomes that can come up, along with their corresponding probabilities. That is what we are calling as the probability distribution function, or a probability function in short. So probably people will write like this, the same thing. So you have to be slightly comfortable in some of the notations. The same thing, what people will write it as is probability that x equal to x is equal to 1 by 6, where x equal to 1, 2, 3, 4, 5, 6. And this is equal to 0 otherwise. Look at it. Is it the same as that table? Right? We are saying probability of x equal to x is equal to 1 by 6. So it need not be represented only in a table form like this. It can be represented in a function form like this. Probability of x being equal to x is 1 by 6. Where x equal to, they have defined these are the values, small x. So probability of x equal to 1 is 1 by 6, x equal to 2 is 1 by 6, x equal to 3 is 1 by 6. So this is what is being coming out, and this is nothing but it's a probability distribution function. And there are two important properties associated with the probability distribution. When I have to say something is a probability distribution function, there are two important things that we have to check. One, each probability which we are identifying here, each probability that is being identified here should lie between 0 and 1, which we already know. Each individual probability should lie between 0 and 1. The other important thing is sum of all these probabilities should be equal to 1, because we are considering all possible outcomes and their corresponding probabilities. And of course, these outcomes should be mutually exclusive also. If one comes, two should not come. So the outcomes all should be mutually exclusive outcomes and their corresponding probabilities. Right? I have to represent these two things. And the two important properties that are very much needed for me is each individual probability should be equal to 1 by 6, and the sum of all the probability, each individual probability should be lying between 0 and 1, and the sum of all the probabilities should be equal to 1. So 1 by 6 plus 1 by 6 plus 1 by 6, up to 6 times if I add, it is nothing but it is equal to 1. Then I am calling some distribution as a probability distribution function itself. If at least one of them is not satisfied, then I don't call it as a probability distribution function. Now let's see one more simple example before we proceed further. Let's say I will give one probability function, P of x equal to x is equal to x by 10, where x equal to 1, 2, 3. Is this a probability distribution? And 0 for otherwise. Is this a probability distribution? Now how do I check it out? Take all the possible values of x. These are the possible values of x. What are their corresponding probabilities? The probability is, we said, x by 10. So if x equal to 1, it becomes 1 by 10. If x equal to 2, it becomes 2 by 10. For x equal to 3, it becomes 3 by 10. Now, the rule, each probability should be between 0 and 1, which is met. Sum of all the probabilities should be equal to 1, which is not the case. 1 by 10 plus 2 by 10 plus 3 by 10, 6 by 10, which is not equal to 1. So sum of all probabilities is not equal to 1 in this case, which means this is not a probability distribution. So though we are seeing it in this kind of a form, we can very well say that this is not a probability distribution function. The same thing probably if it is slightly extended by putting a comma 4. So here x takes even 4 also, and here it becomes 4 by 10, the probability. Now it becomes 10 by 10, which is equal to 1. This becomes a probability distribution function. So this is one thing we have to be comfortable with, identifying whether something is a probability distribution function or not, and by taking all the possible values and their corresponding probabilities. And we should be slowly getting comfortable using this kind of a notation also for the distribution function. It need not be in a tabular form. People can express it in this kind of a function form also for the probability distribution purpose. And so when then we are also talking about cumulative distribution function. Cumulative is nothing but you add up. So we have already made, let's say, the latest example which I have taken, x equal to 1, 2, 3, 4, p of x is equal to 1 by 10, 2 by 10, 3 by 10 and 4 by 10. These are the corresponding probabilities, right? Now when I say cumulative distribution, we are completely talking about adding all the probabilities in the ascending order. So this is nothing but 1 by 10, 3 by 10, 6 by 10, 1. You are adding these two, making it 3 by 10. You are adding this one also to it, making it 6 by 10. You are even adding this one also, making it 10 by 10 or 1. This is actually being written as capital F of x. Cumulative distribution function. So we have to understand whether the question is about probability distribution function or cumulative distribution function. Probability distribution function is the above line, P of x. Whereas cumulative distribution function is f of x. And the simple way we talk about f of x is, this is nothing but probability of x less than or equal to x. X less than or equal to 1. X less than or equal to 2 is 3 by 10. X less than or equal to 3 is 6 by 10. X less than or equal to 4 is 10 by 10 or 1. So when I am trying to plot a graph for this, it means what? Probability of x less than or equal to 1 is 1 by 10. So if you try to plot a graph like this, x being 0, 1, 2, 3, 4. Less than or equal to 1, it is 1 by 10. So you plot the probabilities here, let's say 0.1, 0.2, something like this. You plot it like this. So what you find, less than or equal to 1. So in this entire range, your probability is 0.1. Less than or equal to 2, it is 3 by 10. Right? So between 1 and 2, you are making it around 3 by 10. This is 3 by 10. Less than or equal to 3, it is 6 by 10. 0.6. And less than or equal to 4, it is 10 by 10 or 1. So this is what is your cumulative distribution kind of a function for this example, which is nothing but it is looking like a step function. So most of the cumulative distribution functions are step functions only, because probability cannot be negative. Cumulative distribution function, it only goes up but it can never come down. At the max it can stay flat, but it can never come down because probability can never be a negative value. So it keeps going up, up and up, right? And finally it gets at 1. It gets horizontal at 1. It cannot go beyond 1 also, because the maximum probability possible is equal to 1. So this is how we, for any random variable, we will be looking at, if the question is about finding the probability function, we will look at this. If it is about cumulative distribution function, see, probability function and probability distribution function, both of them are same. If we are talking about cumulative distribution function, then we are looking at this kind of a representation where everything is added up. Right? Then the next important thing for me is a continuous random variable. Just like the way we have looked at discrete. Discrete is slightly comfortable in understanding also, because we are looking at, we know what are the possible values. Only 5, 6. When I have thrown the dice, I know that there are only 6 possible values, right? And I know what are their probabilities easily. But when we talk about a continuous random variable, we actually don't know what could be the possible values, right? Because any value is very much possible. We don't know what are the possible values. So the random variable, because it can take any number of values, any of the values out of the possible, we cannot represent that in a tabular form, right? We cannot represent, because the tabular form is talking of different possible values that it can take and their corresponding probabilities. Whereas the different possible values that can come out in a claim or something. See, if I say number of claims made in a year, probably that can be very much discrete. If you look at it, if my question is about number of claims made in a year, probably I can say 0 claim is possible, 1 claim is possible, 2 claim is possible, and at the max, let's say some 10 claims are possible. I can still look at it as a discrete random variable. But look at claim amount. I don't know, it can be right from 0 to something else. So it has to be a continuous random variable itself. So wherever it is continuous, we don't talk about probability of a value. We will never talk about probability of a value, because at the max 1 or 2 occurrences could be there for that particular value, right? So because so if I say what is the probability of getting 1000.23 or 1000.50 paisa, 1000 rupees 50 paisa as the claim amount, right? Since there are lots of possible values, getting 1000, let's say almost 1 lakh values are possible. 0 to 1 lakh, any number is possible, if I assume. Then probability of getting 1050 may be just 1 by 1 lakh, which is as good as a 0, right? So in continuous random variables, we will not talk about probability of getting a particular value, because in our discrete case, we clearly wrote things like this, right? Probability of x equal to x. Probability of getting one particular value. Whereas in continuous case, I can never write it like that. So in the continuous case, the only possibilities are probability of my x lying between a and b. Only for a range I can talk about. So the probability that the claim amount lies between 1000 and 2000. I will not say the probability of getting 1000 rupees 50 paisa. Right? We'll always talk about, because the chances are very, very slim, and it's as good as a 0. Right? Because so many possible outcomes are there. Probability of getting one single outcome is always 0, almost. I mean, it's a very minute value which can very well be approximated to 0. So that's the reason we will not talk about probability of a single value in a continuous distribution. We will only talk about probability associated with a range or interval of values. Right? So whenever we talk about a probability function, we will not talk about a single value. We will talk about an interval, and which is nothing but, so if I have to arrive at that value of the probability, it is nothing but whatever is the probability curve, we will do the integration of it between the interval value. So when I say the claim amount, the equation of the claim amount is fx, then the probability that the claim is between 1000 and 2000 is, I do an integration between 1000 and 2000, a and b are 1000 and 2000, I do an integration of f of x. That is what is the probability. So in discrete case, it is very easy. We'll get the value straightforward, because total number of occurrences and the number of favorable occurrences. So the probability is easy to obtain in case of a discrete. Whereas in case of continuous, we are actually doing an integration. So basically for doing these probability related numericals, especially for a continuous distribution, a good understanding of the integration as a concept is very much required. Right? Lot of numericals, especially with continuous, all numericals with continuous distribution require the usage of integration to the fullest, because the finding out the probability itself can be done using the definite integral between a and b, integrating the probability function itself. So if someone says, okay, we'll take up a numerical. So any probability that I have to find out, probability function, we are doing it using an integral between a and b. And when I do the same between minus infinity to plus infinity, it's like all possible values. All possible values that that function can take. So the sum which we have done in the discrete case, sum of all possible probabilities should be equal to 1. Here integration of the probability across all possible values should be equal to 1. So this is a rule. In case of continuous, the probability from minus infinity to plus infinity, if I am trying to integrate it, it should be equal to 1 itself. Now let's look at, so probably once we do for one of that, it becomes slightly comfortable for you. See, the continuous random variable, this is having, let's say this is the probability function. It is being given as the probability function is 20 into w cube into 1 minus w square. Now I want to find, and the range, instead of minus infinity to plus infinity, they have simplified it saying that it lies between 0 and 1 itself. Right? So what does it mean? If I do an integration of this particular function between 0 and 1, my sum should come out, my value should come out to equal to 1. Right? Because it lies only between 0 and 1. The integration of this probability function from 0 to 1 should give me the, because these are the all possible values which can be taken up, because they are clearly said that it lies between 0 and 1. So if I integrate it from minus infinity to plus infinity, here I don't need minus infinity to plus infinity because the range is already given. It cannot take anything beyond this. So if I integrate this function, let's say 0 to 1, some common integration formulas, probably it's worth for you to revise. Let's say this, if I integrate it from 0 to 1, so probably I'll take out the constant, I'll expand it, w cube minus w power 5 dw. Now again, the integral of w cube is w power 4 by 4 and w power 5 is w power 6 by 6. Right? So dw, or this is between 1 and 0. So substituting it, it is coming out as 1 by 4 minus 1 by 6. Substituting 1 in place of w, it is giving me 1 by 4 minus 1 by 6. Substituting 0, it is anyhow 0. So probably I am getting it as 12, 3 minus 2, which is 1 by 12 is what I am getting. Okay, so just do a small correction here. Probably instead of 20, you make this 12 only. Yeah, let the numerical be modified. Instead of 20, you make this 12. So what is happening? 12 into 1 by 12. So the sum of all the probabilities is actually coming out to 1. Then you are saying that this is a probability distribution function itself, because the main rule for a probability distribution function is sum of all the probabilities should be equal to 1. In case of continuous, instead of using the word sum of all probabilities should be equal to 1, we say integration of all possible probabilities. Sum is nothing but integration in a continuous case. Integration of all possible probabilities should be equal to 1. So because I am talking about in the range of 0 to 1, I am saying integration between 0 to 1. This particular expansion w cube into 1 minus w squared is what is coming out to, instead of 20 I am taking 12. This entire thing is summation is coming up to 1. That is check for a whether it is a probability distribution function or not. If the question had been 20 w cube, then I will definitely say no, this is not a probability distribution function, because the integration of all the possible values is not coming out to 1. Right? Now, so from there the question is coming out, find the probability of w less than 1 by 4. Right? We know that the w is taking the values between 0 and 1. I want to find out what is the probability that it will take value between 0 and 1 by 4, less than 1 by 4. Right? So for this what will I do? Integral of 0 to 1 by 4, here 12 into w cube minus w power 5. So here I am simply, because I am asking for the value lying between 0 to 1 by 4. The question is anyhow less than 1 by 4. But I know that it lies between 0 and 1. So I am creating the interval saying 0 to 1 by 4. Okay, w power 4 by 4 minus w power 6 by 6. This you are doing an integral between 1 by 4 and 0. So 1 by 4 to the power 4, or probably 0.25 to the power 4 by 4 minus 0.25 to the power 6 by 6. This entire thing you are multiplying this by 12. That is the probability that this lies between 0 and 1 by 4. So you could very well do your calculation. Point 0.25 to the power 6 divided by 6. Right, this is what I'll put it in memory. Then 0.25 to the power 4 divided by 4. So minus whatever is my memory recall, I'll recall that memory. This is what it is. I'll multiply this by 12 and I'll say 0.011. So the probability that the value lies below 1 by 4 is 0.011 itself. The probability that this particular value lies below 1 by 4 is 0.011. Now probably any other question that is being given also, if someone asks you what is the probability that the value lies between 1 by 2 and 3 by 4. Same way. So you put your limits, right? So probability function for you always is, the integration of that function between the two limits. But when we say cumulative function, because it should be right from the beginning up to that. Because in discrete case, what did we do for cumulative? We added up all the possible probabilities. So in the cumulative case, what we'll have to do is, we'll do an integration right from the beginning to that particular value. What is the probability? So So when someone is asking me what is the probability of P of W less than 1 by 4, which is nothing but I can write it as f of 1 by 4 itself. F is like a cumulative, because f, the meaning of that is the probability that x takes a value less than or equal to 1 by 4 up to 1 by 4, right? And that too it is taking the minimum value as 0. So 0 to 1 by 4 is nothing but my cumulative distribution function of f of 1 by 4 itself. So any kind of question that comes up, if the question is about probability distribution function, so because there are few calculations we have to be comfortable with in this. One is a probability distribution function where you do the integration between the values which he is specifying. When he says cumulative distribution function, then you are doing it right from the initial value up to that particular value you are doing the integration. And for discrete case, no harm at all. You will get the calculations very easily done. So first thing is you need to be just comfortable up to doing these kind of calculations for discrete as well as continuous. Two things. First, identify whether the distribution is a discrete or a continuous by knowing what all possible values that the random variable can take. Once you know whether it is discrete or continuous, check out whether you are able to find out the probability distribution function, cumulative distribution function for discrete as well as for continuous. For discrete, the simplicity is in terms of just summing up the things and easily finding out the probability values. Whereas when it comes to continuous, you need to be comfortable with doing the integration part of it, right?